Hello and welcome to Later Night Space. Before settling in, take a quiet moment to like the video and subscribe to the channel. It helps this small, calm corner of the universe reach other nighttime listeners who are searching for something thoughtful and unhurried. And if you feel like it, leave a comment sharing where you're watching or listening from. Tonight, the question is simple. What is the largest thing in the universe? It sounds straightforward, almost innocent, but the moment you begin to answer it, scale starts to slip through your fingers. Planets feel large until compared to stars. Stars feel immense until placed inside galaxies. Galaxies themselves, vast islands of light, gather into clusters. Clusters stretch into superclusters. And beyond them, something stranger emerges. Astronomers have mapped enormous structures called cosmic filaments, immense threads of galaxies woven together into what is known as the cosmic web. They have identified vast formations like the Sloan Great Wall, and even more controversial giants such as the Hercules Corona Borealis Great Wall. Structures so large that they seem to challenge the idea that the universe is smooth on the biggest scales. At some point, structure becomes difficult to define. At some point, thing stops feeling like the right word. Is the largest thing a gravitationally bound object held together by its own mass? Is it a pattern? A statistical overdensity stretched across billions of light years? Or is it the observable universe itself, the entire sphere of space from which light has had time to reach us since the beginning of cosmic expansion? The answer depends on definitions, on physics, on how gravity competes with expansion, on whether dark matter scaffolds these colossal formations into something cohesive, or whether they are simply temporary arrangements inside a much larger, expanding fabric. The deeper you look, the less obvious the answer becomes. And that is where tonight's journey begins. Not with a dramatic explosion or a distant galaxy, but with a quiet shift in perspective. From wherever you are listening right now, a single point on the surface of a small planet orbiting an ordinary star. You are already inside one of these vast structures. You are part of a galaxy, inside a group, inside a supercluster, embedded within filaments that stretch farther than intuition comfortably allows. The question is not only how large the universe can build, it is also whether there is a limit, whether structure eventually dissolves into uniformity, whether there is a scale at which size itself stops making sense. So settle in. Let your thoughts expand at their own pace. There is no rush here. The universe has been building its architecture for billions of years. We can take the time to look at it properly. Tonight, we trace the hierarchy of existence outward, layer by layer, until we reach the edge of structure itself, and see what, if anything, waits beyond it. The deeper this question is examined, the more careful the words have to be. The phrase, largest thing, sounds like it should point to a single object, sitting out there in the dark like a champion with a trophy. But the universe is not always that polite. On the larger scales, it has a habit of turning solid nouns into slippery ideas. In everyday life, a thing is something with edges. A stone has a surface, a house has walls, a river has banks, even if they shift. A planet has a radius that can be measured and a horizon that can be watched at sunset. But in space, boundaries blur. Gravity does not draw crisp outlines with a ruler. It makes gradients, it makes halos, it makes regions where mostly here slowly becomes mostly not here, and that makes the word thing much harder to pin down. So the first step is to choose a definition that physics can defend. In cosmology, the most useful definition is based on gravitational binding. A gravitationally bound system is one where the system's own gravity is strong enough to hold it together over time. Internal motion can be fast and chaotic, but it remains trapped within the same gravitational basin. In other words, the parts can move around, yet the whole does not drift apart. That definition has a practical advantage. It does not rely on whether a structure looks impressive in a picture. It relies on a measurable physical relationship between mass, motion, and gravity. It also gives a clean way to separate an actual object from a mere pattern. A pattern can be real and meaningful, but it may not be bound. It may be a temporary arrangement that is slowly being stretched apart by the expansion of the universe. Gravity, then, is the sculptor. But gravity does not work alone. The universe expands, and that expansion matters more and more as distance increases. Edwin Hubble's observations in 1929 showed that distant galaxies are receding, with more distant galaxies receding faster. The phrase, "the universe expands," is not just poetry. It means that space itself stretches, carrying galaxies along with it on the largest scales. So the question becomes two questions sitting quietly inside one sentence. What is the largest gravitationally bound structure? And what is the largest identifiable structure, even if it is not bound as a whole? Those two answers may not be the same. To keep everything grounded, it helps to begin with a ladder of scale that starts where intuition still works. Earth is a clear example of a bound thing. It has a diameter of roughly 12,000 kilometers. Its gravity holds an atmosphere, an ocean, and a crust that mostly stays put, despite the occasional complaint from plate tectonics. Earth's gravity is strong enough that the average gas molecule does not simply drift away into space. A few particles escape, but the system remains coherent. Earth is a thing in the simplest possible sense. Now step outward to the Sun. The Sun's diameter is a bit over 100 times Earth's, and its mass is more than 300,000 times greater. It is a gravitationally bound sphere of plasma. If gravity were the only factor, the Sun would collapse inward. But the Sun has an internal engine. In its core, nuclear fusion converts hydrogen into helium, releasing energy. Hans Bethe laid out the core ideas of stellar fusion in the 1930s, explaining how stars can shine for billions of years rather than burning out in a cosmic afternoon. The Sun stays stable because of hydrostatic equilibrium. Gravity pulls inward, while pressure from the hot, dense interior pushes outward. Energy generated in the core moves outward through radiation and convection, eventually reaching the surface and streaming into space as sunlight. The principle behind the energy release is the one associated with Albert Einstein's mass-energy equivalence, expressed as energy equals mass multiplied by the speed of light squared. A tiny amount of mass becomes energy, and that energy helps keep the star from collapsing. The Sun is not just a ball of fire. It is a balanced argument between gravity and pressure, and the argument has been running for about 4.5 billion years. Even at this point, the ladder is already climbing faster than the mind prefers. But the next step is where the numbers stop feeling like everyday measurements and start feeling like geography written by someone who enjoys practical jokes. The Sun is one star among hundreds of billions in the Milky Way galaxy. The Milky Way is a gravitationally bound system of stars, gas, dust, and something stranger and more important than it first appears. The visible part of the Milky Way, the bright disk and its spiral structure, stretches roughly 100,000 light-years across. A light-year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, which means a light-year is close to 10 trillion kilometers. 10 trillion is not the kind of number that fits comfortably into a human day, but it is an honest one. The Sun orbits the center of the Milky Way, taking roughly 230 million years to complete a single circuit. That orbit is not a simple path around a neatly marked central dot. It happens inside a rotating galaxy with spiral density waves, star-forming regions, and vast clouds of gas. At the center lies a supermassive black hole known as Sagittarius A star, with a mass of roughly 4 million suns. The orbits of stars near the galactic center, measured over decades, show that an enormous compact mass must be there. The Milky Way is not held together by its visible stars alone. It is held together by an invisible halo of dark matter. Dark matter is one of the major reasons the phrase "largest thing" gets complicated. Dark matter does not emit light and does not absorb light in the way ordinary matter does. It reveals itself through gravity. Fritz Zwicky, studying the Coma cluster in the 1930s, noticed that galaxies were moving too fast to be held together by the visible mass alone. He inferred missing mass, a kind of unseen matter that provided extra gravity. Decades later, Vera Rubin's measurements of galaxy rotation curves in the 1970s showed the same problem on the scale of individual galaxies. Stars far from the center orbit too quickly for the visible matter to explain. The implication is that galaxies sit inside large dark matter halos that extend far beyond the visible disk. This matters for the definition of a thing. A galaxy does not have a sharp edge like a planet. Its star density gradually thins. Its gas becomes more sparse. Its dark matter halo fades outward in a long, extended profile. The galaxy is still a bound system, but its boundary is a gradient rather than a wall. If someone asked where the Milky Way ends, an honest answer would involve a pause, a deep breath, and a gentle reminder that nature rarely draws with hard lines. Still, the Milky Way is a coherent object in the gravitational sense. Most of its stars are bound to it. Its structure persists over billions of years. It evolves, merges, forms new stars, and reshapes its spiral pattern, but it remains a single gravitational system. On this ladder, the Milky Way is the first scale where thing begins to feel less like a rock and more like a region of influence. This is also the point where the universe begins to feel like architecture. Not architecture made of stone and steel, but architecture made of mass and motion, of gravity and time. A planet is a sphere, a star is a sphere, a galaxy is a rotating disk with a halo. The shapes become more diverse and the forces become more subtle. And yet, even this is not the upper end of things that are clearly physically real. There are larger structures than a galaxy, and some of them are bound and some of them are not. The crucial idea is that as the scale increases, the universe shifts from objects that are obviously cohesive to structures that are cohesive only in parts, and then to structures that are coherent mostly as statistical patterns. Before climbing further, it helps to name the tension clearly. Gravity binds, cosmic expansion separates. Both are real. both operate at once. At small scales, gravity dominates and expansion is negligible. At very large scales, expansion dominates, and gravity struggles to assemble ever larger unified systems. The boundary between those regimes is where many of the largest structure headlines live, and it is also where definitions begin to matter more than excitement. So the ladder begins like this. Earth is bound, the Sun is bound, the Milky Way is bound. The binding is not identical in each case, but the principle is consistent. The system's own gravity keeps it together. That is a workable foundation for the word thing. There is one more quiet complication that sits behind the scenes. Even the phrase largest can mean different things. Largest by diameter is not the same as largest by mass. Largest by gravitational influence is not the same as largest by physical extent. A dark matter halo can extend far beyond visible stars. A region can be enormous but contain very little matter. A structure can be visually striking and still not be bound as a whole. Cosmology is full of these slightly awkward trade-offs, as if the universe insists on keeping its trophies in different rooms. For now, the goal is not to choose the winner prematurely. The goal is to define the competition. The simplest, most physically defensible answer to what is the largest thing will be the largest gravitationally bound structure. That is the category where the word thing behaves most like it does on Earth. But because the universe also produces enormous connected patterns that may not be bound as single units, there will be a second category as well, where thing starts to mean largest identifiable structure in the cosmic web. Both answers can be true at once, as long as the definition is stated plainly. With that foundation set, the next rung on the ladder is ready. The Milky Way is not alone. Galaxies gather, they orbit shared centers, they fall together, they collide in slow motion, they build larger structures, and in doing so they carry the definition of thing to the edge of where gravity can still claim ownership. And somewhere out there, beyond the comforting boundaries of planets and stars, the universe offers a test. A test of how big a structure can become before the word thing starts to lose its meaning. A galaxy is often described as an island of stars, but that phrase is almost too gentle for what it really is. A galaxy is a rotating, self-contained gravitational ecosystem. It is built from ordinary matter, like hydrogen gas and starlight, but it is also built around an invisible framework that does most of the heavy lifting. That framework is the dark matter halo, a vast distribution of mass that extends far beyond the visible stars and gives the galaxy much of its gravitational grip. This invisible halo matters because it solves a problem that would otherwise make galaxies hard to keep. If gravity came only from the stars and gas that can be seen, then many galaxies would not rotate the way they do. In the 1970s, Vera Rubin measured the rotation curves of spiral galaxies and found something deeply revealing. Stars far from the galactic center orbit at speeds that stay surprisingly high, instead of dropping off the way they would if most of the mass were concentrated in the luminous core. The simplest interpretation is that there is far more mass than what telescopes can see, spread out in an extended halo. It is not a small correction, it is the main event. Once that halo is included, the galaxy becomes a stable thing in the gravitational sense. Stars orbit within a shared potential well. Gas clouds drift, collide, and collapse. New stars are born, old stars die, and the galaxy quietly rearranges itself over billions of years. It is not static, but it is coherent. Even the most dramatic galactic events, like the collision of two large galaxies, are not typically collisions between individual stars. The distances between stars are so enormous that most stars pass by without direct impact. Instead, the real violence happens through gravity, tidal forces, shock waves in gas, and bursts of star formation. The galaxy changes shape, but the system remains governed by gravity and remains, in the end, a single bound structure. Within the Milky Way, this slow choreography is happening all the time. Star-forming regions light up where gas collapses. Supernova explosions enrich the interstellar medium with heavier elements. Stellar winds carve bubbles in gas clouds. The galaxy is a living system, but the living part is not biology. It is gravity and thermodynamics, patiently shaping matter across deep time. Yet galaxies rarely live alone. Gravity encourages company. The Milky Way is part of a small gravitational community known as the local group. This is where the definition of thing begins to stretch again, because now the thing is no longer a single halo with a single luminous disk. It is a region of space where multiple galaxies share a gravitational fate. The local group includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. The dwarf galaxies are especially telling because they behave like gravitational test particles. Their motions trace the deeper mass distribution of the local group, much of which is dark matter. The local group spans roughly 10 million light-years. That is already 100 times the diameter of the Milky Way's bright disk, and it is still considered a relatively small association by cosmic standards. The relationship between the Milky Way and Andromeda is one of the clearest examples of a bound future on a grand scale. Andromeda is the nearest large spiral galaxy to the Milky Way, and it is not simply drifting away with cosmic expansion. It is moving toward us. Its approach is a reminder that cosmic expansion does not dominate everywhere. Where gravity is strong enough, structures pull together despite the overall stretching of space. Measurements of Andromeda's motion show that it is approaching at roughly a few hundred kilometers per second along the line of sight, and that its sideways motion is small enough that a merger is likely. In about 4 to 5 billion years, the Milky Way and Andromeda are expected to merge into a single, larger galaxy. This future system is sometimes nicknamed Milkomeda in popular explanations, which sounds like a dessert brand, but it is a real gravitational prediction. The merger will unfold over hundreds of millions of years. Spiral structures will distort. Tidal tails of stars will stretch outward. Gas clouds will collide and ignite bursts of star formation. Over time, the merged system may settle into a more elliptical shape. Through all of that, the local group remains a thing in the gravitational sense. It is bound. Its members orbit within a shared gravitational environment. It has a fate that is not defined by cosmic expansion, but by local gravity. This is a crucial point because it shows that the universe contains multiple regimes at once. On the larger scales, galaxies recede from one another as space expands. On smaller scales, gravity overrides expansion and pulls matter together. The next step outward is where the word largest starts to feel more serious. Beyond small groups of galaxies lie galaxy clusters, and clusters are among the most massive gravitationally bound structures known. If the question is, what is the largest thing in the universe in a strict, physically cohesive sense, clusters immediately rise to the top of the candidate list. A galaxy cluster can contain hundreds to thousands of galaxies. It also contains something less visible but equally important, an enormous reservoir of hot intra-cluster gas. This gas is so hot, often tens of millions of degrees, that it emits X-rays. That is one reason cluster studies became far more powerful with X-ray astronomy. NASA's Chandra X-ray Observatory, along with the European Space Agency's XMM Newton, has revealed clusters as glowing giants with hot gas filling the space between galaxies, like a vast atmospheric sea. Clusters also contain vast amounts of dark matter, far more than the mass in stars and gas. In the 1930s, Fritz Zwicky studied the Coma cluster and noticed that the galaxies were moving too fast to be held together by visible matter alone. His conclusion was that there must be missing mass, a form of unseen matter that provided extra gravity. That insight, though not fully accepted at the time, was one of the earliest strong arguments for what is now called dark matter. Coma remains a classic example because it is rich, massive, and relatively nearby by cosmological standards. It contains more than 1,000 galaxies and has a total mass on the order of 1 quadrillion times the mass of the Sun. Most of that mass is not in the galaxies that can be seen. It is in the dark matter halo of the cluster itself. The galaxies are like luminous beads embedded in a much larger invisible structure. This is where another phenomenon becomes important: gravitational lensing. According to Albert Einstein's general theory of relativity, mass and energy curve space-time, and light follows those curves. In the presence of a massive cluster, light from background galaxies can be bent enough to distort their images. Astronomers see arcs, stretched smears, and sometimes near rings of light. These effects are not just visual curiosities. They allow the distribution of mass inside the cluster to be mapped directly, including the distribution of dark matter. There are two main forms of lensing used in practice. Strong lensing produces dramatic arcs and multiple images when alignment is especially favorable. Weak lensing produces subtle statistical distortions across many background galaxies, requiring careful measurement and averaging. Together, these techniques provide some of the most direct evidence that clusters are dominated by unseen mass. Clusters can also reveal their mass through the motions of galaxies inside them. Galaxies in a cluster do not orbit in neat circles. They move in complex paths through the cluster's gravitational potential. Their typical speeds can be on the order of 1,000 kilometers per second. Those speeds are a measure of the cluster's mass. If the mass were too small, the galaxies would escape. The fact that they remain bound tells you, in the bluntest possible way, that the cluster's gravitational well is deep. And clusters have another feature that makes them feel like a genuine answer to the original question. Unlike superclusters and great walls, clusters are unambiguously gravitationally bound as whole systems. Their cohesion is not a statistical impression, it is physical. If the universe expands forever and if dark energy continues to accelerate that expansion, a massive cluster will still remain a cluster. It may merge with neighboring groups. It may accrete matter along filaments, but it will not dissolve into the general expansion of space. This makes the cluster category particularly important for the phrase largest thing. It is the largest scale at which gravity's ownership is not disputed. Planets are bound, stars are bound, galaxies are bound, groups are bound, clusters are bound. Each step grows larger by orders of magnitude, but the definition remains stable. Gravity dominates internal dynamics. The system stays together. At this point, the universe offers a kind of choice about what counts as an answer. If the goal is a single, cohesive, physically bound structure, then clusters are a strong contender for the title. They are enormous. They are long-lived. They are definable. They have measurable mass and extent. Their membership is not merely an artifact of how a map is drawn. It is enforced by gravity. But if the goal is the largest identifiable structure in the sense of the largest pattern in the galaxy distribution, then clusters are only the beginning. They are nodes. They sit at intersections. They are the densest gatherings in a larger network. That larger network reveals itself when clusters are plotted in 3 dimensions, across huge volumes of space. Clusters are not evenly scattered. They are arranged along filaments. They are connected by bridges of galaxies and dark matter. Between them lie vast, underdense regions called cosmic voids. This is the first hint that the universe has a kind of skeletal architecture, with clusters acting like joints. Even within the local group, the idea of connected structure is visible in a small way. The Milky Way and Andromeda are not just neighbors. They share a gravitational environment. Their dark matter halos may already be interacting at the edges, long before the galaxies themselves merge. On cluster scales, these interactions and connections become part of a larger pattern, one that begins to look less like a collection of separate objects and more like a connected landscape. Still, it is worth lingering for a moment on the sheer audacity of a galaxy cluster as a physical object. A planet is measured in thousands of kilometers. A star is measured in millions of kilometers. A galaxy is measured in tens of thousands of light years. A cluster can span millions of light years, contain thousands of galaxies, and hold enough mass to bend space-time visibly. If a cluster were a character in a story, it would be the quiet giant who does not speak much, but whose presence changes the geometry of the room. And yet, even that giant sits inside something larger. As maps of the universe widened, clusters were seen to gather into larger associations. This is where the neatness of gravitational binding begins to fray, and where the word thing starts to take on a softer meaning. The next step outward is not just bigger, it is different. It is the point where gravity and cosmic expansion begin to compete in earnest, and where the universe stops offering clean boundaries and starts offering gradients, flows, and immense connected patterns that may not remain together forever. For now, though, the ladder is steady. Galaxies are bound islands built on dark matter scaffolds. Groups are bound communities with shared futures. Clusters are bound giants, deep gravitational basins filled with galaxies, hot gas, and unseen mass. If a strict, physically cohesive answer is required, clusters are already an impressive place to stop. But the universe does not stop there. It rarely does. A galaxy cluster feels like a satisfying answer because it behaves like an object. It has a shared gravitational basin. It has a measurable mass dominated by dark matter. It has hot intracluster gas that glows in X-rays. It can bend the path of light through gravitational lensing. It has member galaxies moving at high speeds that still cannot escape. In other words, it looks like a thing in every physically meaningful sense. And then the universe does what it often does. it keeps building. When astronomers began mapping the distribution of galaxy clusters across larger and larger volumes of space, they noticed that clusters themselves are not scattered randomly, like salt thrown over a table. They gather into larger associations. These associations are called superclusters, and they can span hundreds of millions of light years. A supercluster is not simply a bigger cluster. It is a new kind of structure, one that sits right on the boundary between two regimes. Below this scale, gravity holds things together decisively. Above this scale, the expansion of the universe begins to compete in a serious way. That competition is the heart of the supercluster story. The word supercluster can sound like a neat category, as if it were a well-defined object with a clean outline. In reality, superclusters are often more like regions of influence. They are large areas where galaxy clusters and smaller groups appear to be associated, sometimes connected by filaments, sometimes sharing a common flow of motion, and sometimes simply sitting in the same broad, overdense region of the cosmic web. This is where the idea of defining a thing by boundaries becomes difficult. A galaxy cluster can be described as a deep gravitational well. A supercluster can be described as a landscape of wells, hills, ridges, and valleys. It is less like a single bowl and more like a whole mountain range. A useful way to think about it is to imagine a sheet of space in which matter creates depressions. A cluster is a strong, deep depression. A supercluster is a wide area where multiple depressions overlap and where the terrain slopes towards certain basins. Galaxies and clusters move across that terrain, influenced by gravity, but also carried by the overall expansion of space. This is why superclusters are often studied not only by where galaxies are, but by how they move. In 2014, a team led by Brent Tully published work that helped redefine how a supercluster can be drawn. Instead of merely outlining a region of higher galaxy density, they used velocity flow mapping. The idea is simple in spirit, even if the data analysis is not. Galaxies do not only participate in the Hubble flow, the general recession caused by cosmic expansion. They also have peculiar velocities, additional motions caused by gravitational attraction toward mass concentrations. If a region of space acts like a common gravitational basin, then galaxies within that region tend to stream toward the same attractor. By measuring these motions, one can trace the boundaries of a gravitational watershed. Using this approach, Tully and colleagues described the Laniakea supercluster, a vast region roughly 500 million light-years across that contains around 100,000 galaxies, including the Milky Way. The name Laniakea comes from the Hawaiian language and is often translated as immense heaven, which is both poetic and accurate in the most literal sense. A structure spanning hundreds of millions of light-years is not just large. It is the kind of large that forces the mind to change gears. But Laniakea also reveals the problem with calling a supercluster a single thing. The region can be defined by flow, by the direction galaxies are moving under gravity, but that does not guarantee that the entire structure is gravitationally bound in the way a cluster is bound. Some parts of Laniakea are strongly bound, especially dense clusters and their surroundings. Other parts are more loosely associated. Over very long timescales, the expansion of the universe may pull the outer regions away faster than gravity can hold them in. This is the quiet turning point in the original question. A galaxy cluster is a bound object. A supercluster can be partly bound, partly transitional, and partly a pattern that is still evolving under competing influences. The word thing still applies, but it applies more softly. To see why, it helps to return to the idea of expansion, but with a slightly sharper focus. On the larger scales, galaxies recede from one another because space itself expands. Edwin Hubble's work in the early 20th century showed that recession speed increases with distance. In concept, the relationship can be expressed as recessional speed equals the Hubble constant multiplied by distance. The important point is not the exact numerical value in this moment, but what the equation means physically. The farther away something is, the more of the expanding space lies between here and there, and the faster that distance grows. Inside a bound system, gravity dominates, and expansion does not tear it apart. That is why atoms, solar systems, and galaxies are not being stretched like taffy. But as distance scales increase, gravity becomes less able to keep the entire region cohesive. Superclusters exist in the zone where gravity still matters strongly, but not strongly enough to guarantee permanent unity across the whole structure. This is also why the idea of the largest thing can produce multiple honest answers. If the largest thing must be bound, clusters are the strongest candidates. If the largest thing can be an extended association, a gravitational watershed, or an overdensity that will not remain unified forever, then superclusters enter as contenders. And beyond superclusters, the picture changes again, because superclusters are not isolated islands either. They are part of a larger architecture. When astronomers map the distribution of galaxies and clusters across truly enormous volumes, the universe reveals a filamentary structure. Galaxies gather along threads. Clusters sit at intersections like knots in a net. Between them are vast voids with far fewer galaxies. This pattern is called the large-scale structure of the universe, and its most common nickname is the cosmic web. The phrase cosmic web can sound like a metaphor, but it is not a metaphor in the casual sense. It is a description of the observed geometry of matter distribution. It is also a prediction of modern cosmology, and it emerges naturally from the physics of gravitational collapse operating over billions of years. The cosmic web is made of three broad components. There are filaments, long strands where galaxies are more likely to be found. There are nodes, where filaments intersect and where massive clusters tend to form. And there are voids, enormous regions of relatively low density. Voids are not empty like a vacuum chamber on Earth, but they are dramatically underdense compared to filaments and clusters. They can span tens of millions of light years, sometimes even more. If clusters are the densest knots, filaments are the connective tissue. A filament may stretch across hundreds of millions of light years, with galaxies and groups strung along it like lights on a long, dark wire. Matter does not distribute itself evenly because gravity amplifies differences. A slightly denser region attracts more matter. That additional matter increases density further. Over time, the contrast grows. This process is known as gravitational instability. It is one of the simplest and most powerful ideas in cosmology. Start with a nearly uniform medium with tiny density fluctuations. Gravity pulls more matter into the slightly denser regions. Those regions become denser still. Over long timescales, the medium develops structure. In the universe, this process has been running for billions of years, and it has built the web. The cosmic web also makes clear why dark matter is so central. Dark matter does not interact with light in the normal way, so it does not radiate energy and cool into a disk the way ordinary gas can, but it does respond to gravity. In the early universe, dark matter began clumping first, forming halos and filaments as the dominant mass component. Ordinary matter, often called baryonic matter, fell into those gravitational potentials. Gas collected, cooled, and formed the first stars and galaxies. In this sense, the luminous universe traces the underlying dark matter scaffold. This picture is not only inferred from observation, it is reproduced in computer simulations with striking realism. One of the most influential examples is the Millennium Simulation, run by researchers associated with the Max Planck Institute for Astrophysics. The goal of such simulations is to start with early universe conditions consistent with observations, and then let gravity build structure forward in time. When the initial conditions match what is measured in the cosmic microwave background, the simulation evolves into a web of filaments and clusters that resembles what sky surveys actually map. It is difficult to overstate how significant this is. The cosmic web is not just a pretty pattern, it is a test of the model. The fact that the model produces the web suggests that the broad story is correct. Small initial fluctuations, amplified by gravity, shaped by dark matter, and evolving within an expanding universe. But where did those initial fluctuations come from? The early universe was remarkably uniform. Measurements of the cosmic microwave background radiation showed temperature variations that are tiny compared to the average temperature. The best-known high-precision map comes from the Planck satellite, operated by the European Space Agency. Planck measured anisotropies at a level of only a few parts in 100,000. Those anisotropies represent density differences in the early universe, the seeds of all later structure. The leading explanation for the origin of those seeds is cosmic inflation, a rapid expansion phase proposed by Alan Guth in 1980 and developed further by André Linde and others. During inflation, quantum fluctuations were stretched to cosmic scales. After inflation ended, those fluctuations remained imprinted in the matter and energy distribution of the universe, later appearing in the cosmic microwave background, and then growing into galaxies, clusters, and filaments. Even without diving into every detail of inflation, the takeaway is gentle and profound. The largest structures in the universe began as tiny differences. The universe built its vast architecture from very small starting points, given enough time and gravity. Time is the other quiet architect here. The universe is about 13.8 billion years old. That is long enough for gravity to turn small contrasts into large structures, but not long enough for anything to grow without limit, especially because expansion and, later, dark energy act as a brake. And this is where the cosmic web changes the meaning of the word thing again. A filament can be enormous. A supercluster can be enormous. But neither is necessarily bound as a whole in the way a cluster is bound. They are coherent in the sense that they trace the same large-scale pattern, but their long-term fate is not to remain as a single, unified object. Over deep future time, expansion will stretch these connections. Some regions will remain bound, like clusters. Others will slowly drift apart, and the web will thin. So if the definition of the largest thing is based on boundness, the cosmic web is too large and too diffuse to qualify as a single object. It is not one gravitational basin, it is a network of basins connected by ridges of higher density. Yet if the definition allows the largest identifiable structure in the distribution of matter, the cosmic web becomes the central stage on which every other candidate stands. The web also gives context to the next set of extreme claims, the ones that tend to produce headlines. Great walls, enormous arrangements of galaxies stretching across 1 billion light-years or more, are not separate from the web. They are features within it. They are especially extended over dense regions like long ridges in the terrain. But before reaching those named giants, it is worth lingering for a moment on what the cosmic web implies about meaning. The universe does not arrange itself into a neat hierarchy of nested spheres. It makes networks, it makes filaments, it makes voids, it makes knots, it makes structures that look less like objects and more like geography. This is why the original question, what is the largest thing in the universe, keeps evolving. The biggest bound objects are one category. The biggest connected patterns are another. The most extreme over densities are a third. And the observable universe itself is a different kind of boundary, defined by what light can reach rather than by what gravity can hold. Still, even with all these categories, the cosmic web offers something steady and calming. It shows that the universe is not random. It is structured not by design, but by simple physical laws. Gravity amplifies differences. Dark matter provides scaffolding. Ordinary matter follows. Expansion stretches the whole process across time, and the result is a web that is both elegant and indifferent, shaped by physics rather than intention. And within that web, superclusters like Laniakea are immense watersheds of motion, where galaxies stream along the slopes of gravity's landscape. Clusters are deep wells at intersections. Filaments are the bridges. Voids are the quiet spaces between. The universe is not a collection of isolated islands. It is a connected terrain. The ladder has now reached a point where scale and definition start to pull against each other. The structures are getting larger, but the word thing is getting less certain. The next step outward will not just be bigger. It will be more controversial because it will involve structures that test the idea that the universe becomes smooth on the largest scales. In other words, the universe is about to offer its boldest candidates, the ones that force cosmologists to ask not only how large a structure can be, but whether a structure of that size should exist at all. Once the cosmic web is seen as the universe's underlying architecture, it becomes easier to understand why astronomers began hunting for its most extreme features. If galaxies and clusters trace filaments, and filaments outline a vast network, then some parts of that network should be thicker, longer, and more concentrated than others. The question is how thick and how long they are allowed to be before they start to challenge the idea that the universe becomes smooth on the largest scales. Finding those extremes requires turning the night sky into a three-dimensional map. In 2 dimensions, the sky is a dome of points. A galaxy might look close to its neighbor simply because they sit near each other on the sky, even if one is far behind the other. To identify true structure, distance must be measured, not guessed. That is where redshift becomes essential. Redshift is the stretching of light toward longer wavelengths as space expands. In an expanding universe, a galaxy's light arrives slightly stretched, and the amount of stretch generally increases with distance. The relationship between distance and recession is often summarized by the idea behind Hubble's law, expressed as recessional speed equals the Hubble constant multiplied by distance. The important part for mapping is that redshift can act as a distance proxy. If the redshift is known, the galaxy can be placed in a rough, three-dimensional position relative to Earth. This method is not perfect. Galaxies also have peculiar velocities, additional motions caused by gravity, which can slightly distort redshift-based distance estimates, especially nearby. But over very large distances, redshift becomes a powerful mapping tool. It turns a flat star map into a volume. This is why large redshift surveys changed cosmology. Instead of studying galaxies one by one, astronomers began to chart the galaxy distribution across huge regions. The Sloan Digital Sky Survey, often shortened to SDSS, became one of the most influential efforts of this kind. Using a dedicated telescope at Apache Point Observatory in New Mexico, SDSS measured the positions and redshifts of vast numbers of galaxies, creating one of the richest three-dimensional maps of large-scale structure ever assembled. It was not merely a catalogue, it was a new way of seeing the universe. When those galaxy positions were plotted, the cosmic web emerged with startling clarity. Filaments and sheets became obvious. Voids appeared as enormous low-density cavities. Clusters showed up as dense knots. And within that landscape, astronomers began to identify particularly extended, overdense features, structures that looked like long ridges in the cosmic terrain. One of the most famous of these discoveries is the Sloan Great Wall. In the early 2000s, researchers analyzing SDSS data described an immense structure spanning roughly 1 billion light-years. Among the names associated with the announcement is J. Richard Gott, whose work helped frame the discovery in the language of large-scale structure and statistical analysis. The label Sloan Great Wall was not meant to imply a literal wall in the everyday sense. No solid barrier exists. Instead, this was a vast connected overdensity, a region where galaxies, groups, and clusters were arranged in an extended, unusually large pattern within the cosmic web. To appreciate what 1 billion light-years means, it helps to return briefly to the ladder that began with planets and stars. The Milky Way is about 100,000 light-years across in visible starlight. A galaxy cluster might span a few million light-years. A supercluster like Laniakea spans hundreds of millions of light-years. The Sloan Great Wall, at around 1 billion light-years, is larger than many superclusters and stretches across a distance that begins to feel uncomfortably close to the scale where cosmologists expect the universe to become homogeneous. Homogeneity does not mean that every region is identical in detail. It means that if an observer averages matter density over large enough volumes, the average approaches the same value everywhere. This expectation sits at the heart of the cosmological principle, which states that the universe is homogeneous and isotropic on sufficiently large scales. The phrase sufficiently large is doing a lot of work here. The Sloan Great Wall lives right near the zone where that phrase becomes critical. So the first reaction to such a discovery is not only awe, it is also a careful question. Is this structure genuinely a single coherent feature, or is it an artifact of the way the map is sampled and drawn? Is it something that would still stand out if the survey were even larger, or would it blend into a broader pattern once more data is added? These questions are not nitpicking. They are what it means to do cosmology responsibly. On these scales, the universe is not a set of neatly bounded objects. It is a statistical field. What looks like a single long wall might be several structures aligned in a way that appears more unified than it truly is. Or it might be a genuine extreme overdensity produced by the random distribution of primordial fluctuations that were later amplified by gravity. The Sloan Great Wall was discovered through direct galaxy mapping, which is a significant point in its favor. Unlike some proposed structures inferred from rarer tracers, this one emerges from millions of galaxy measurements with redshift information, a dataset designed specifically to measure large-scale structure. It is still a complex structure with ambiguous edges, but it is grounded in the most direct type of mapping cosmology has available. Even so, the phrase Great Wall can mislead if taken too literally. A better mental image is a long ridge made of many peaks and valleys. Along the ridge are galaxy clusters and rich galaxy groups. Between those dense nodes are filaments, regions where galaxies are more common than average. Surrounding the ridge are lower density regions and voids. The wall is not a uniform slab. It is a connected overdensity embedded in the cosmic web's broader network. And now the question returns, sharpened by scale. Is the Sloan Great Wall a thing? If the definition requires gravitational binding as a single cohesive unit, then the answer is no. A structure 1 billion light-years long cannot be gravitationally bound as one object under the standard cosmological model. Cosmic expansion acts across that scale. The wall does not have a single gravitational center holding its entire extent together. Its clusters may be bound individually. Some smaller components may be bound. But the entire wall is not a single bound system in the way a cluster is. If the definition allows the largest identifiable structure in the distribution of matter, then the answer becomes more interesting. In that sense, the Sloan Great Wall is undeniably a structure. It is a feature of the cosmic web mapped by a major survey, with a scale that makes it one of the largest known formations traced directly by galaxies. This is where cosmology often asks a second type of question. Not is it bound, but is it statistically consistent with the standard picture of the universe? The standard picture begins with a nearly uniform early universe, with tiny density fluctuations. Those fluctuations were measured in the cosmic microwave background radiation, mapped in high precision by missions such as the Planck satellite, operated by the European Space Agency. Those small fluctuations were then amplified by gravity over billions of years, building galaxies, clusters, and the web itself. When cosmologists simulate this process using the lambda cold dark matter model, they get a cosmic web, and they also get occasional large overdense features. The universe is allowed to have extremes, as long as those extremes are rare enough. In other words, homogeneity does not forbid big structures. It sets expectations for how common they should be and how the distribution of sizes should behave. A single rare structure can exist without breaking the overall statistical smoothness. This is similar to the idea that an ocean can be mostly calm, while still producing occasional large waves. The ocean remains an ocean, and the wave remains a real wave, but the existence of a big wave does not mean the ocean has become a wall. The Sloan Great Wall is often discussed in precisely this way. It is enormous and it sits near the upper end of the expected distribution, but it does not necessarily violate the cosmological principle. It is a large statistical overdensity, not a universe-breaking contradiction. Its existence pressures theorists to check their assumptions and refine their statistics. but it does not automatically force a rewrite of cosmology. That distinction matters because it changes the tone of the question. The largest structures are not necessarily paradoxes. They are often the most dramatic examples of the same physics that builds everything else. Gravity amplifies small differences. Dark matter provides scaffolding. Ordinary matter follows. Cosmic expansion stretches the whole pattern. Dark energy slows the growth of the very largest structures over time. The Sloan Great Wall can be seen as a natural outcome of that long process, an extreme ridge in a vast terrain. It also matters because it acts as a gateway to the next rung. The Sloan Great Wall is the first named megastructure that many people encounter in this topic, because it is directly connected to one of the best-known surveys in astronomy, and because its scale is so large that it feels almost absurd. But it is not the end of the story, and it is not the most controversial claim. The Sloan Great Wall is built from galaxies and clusters, mapped in a systematic redshift survey. That gives it a kind of observational solidity. It is a ridge the map can point to. The next candidate, however, is inferred in a different way, using rare explosions as beacons across deep time. And because of that, it comes with a different kind of uncertainty. For now, the Sloan Great Wall stands as a remarkable marker on the edge of intuition. It is not a single bound object, but it is a real structure in the distribution of matter. It demonstrates how far the cosmic web can stretch before the universe begins to smooth out. It is a reminder that large-scale structure is not a metaphor. It is geography written in galaxies. And it leaves a quiet question hanging in the air. If a galaxy survey can reveal a wall 1 billion light-years long, what happens when the universe is probed with tracers visible across even greater distances, where the map becomes thinner, noisier, and potentially more surprising? The next candidate is harder to hold in the hand because it is not drawn primarily from a dense grid of galaxy positions. It is inferred from flashes, brief, violent beacons that erupt in distant galaxies, shine across a large fraction of cosmic history, and then vanish before anyone has time to get comfortable. These beacons are gamma ray bursts. A gamma ray burst is one of the most energetic events known in the universe. In a matter of seconds, a single burst can release as much energy as the sun will emit over billions of years, at least in gamma rays alone. The exact mechanisms depend on the type of burst, but the broad picture is now well established. Long-duration gamma-ray bursts are commonly linked to the collapse of very massive stars, events often called collapses, which can also produce certain kinds of supernovae. Short-duration gamma-ray bursts are strongly associated with mergers of compact objects, especially neutron star mergers, which were dramatically confirmed when gravitational waves and electromagnetic signals were observed together in a famous multi-messenger event detected by the Laser Interferometer Gravitational Wave Observatory and Virgo in the late 2010s. Whatever the engine, the useful feature for cosmology is the same. Gamma-ray bursts are extremely bright and can be seen from very far away. That makes them tempting tools for probing structure at scales where ordinary galaxy surveys become more difficult. A galaxy survey needs to detect many faint galaxies and measure their redshifts, which becomes challenging at very large distances. Gamma-ray bursts announce themselves. They flare and they do not ask permission. NASA's Swift Observatory, launched in the mid-2000s, was designed to detect gamma-ray bursts quickly and then turn its instruments to capture their afterglows at X-ray and optical wavelengths. That afterglow is crucial because it allows astronomers to identify the host galaxy and measure the redshift. With enough bursts and enough redshift measurements, one can place these explosions in three-dimensional space, not with the dense completeness of a galaxy survey, but with a sparse set of points scattered across vast distances. That sparseness is both the strength and the weakness of the method. It is a strength because the points reach far. It is a weakness because there are not many of them. And when you try to infer the shape of a structure from a small number of points, the human brain becomes an over-enthusiastic pattern detector. It loves to connect dots even when the dots are few. Still, the idea is scientifically legitimate. If matter is distributed in a cosmic web, then the galaxies hosting gamma-ray bursts should also trace that web. If a region is overdense in galaxies, it might also be overdense in gamma-ray bursts, simply because there are more galaxies there to produce them. In principle, the distribution of bursts could reveal large-scale structure, especially at distances where galaxy catalogues thin out. This is where the Hercules Corona Borealis Great Wall enters the story. In the early 2010s, researchers analyzing the positions and redshifts of gamma-ray bursts reported an apparent clustering of bursts in a particular region of the sky. The region lies in the direction of the constellations Hercules and Corona Borealis, which is where the name comes from. The inferred structure, based on the concentration of bursts at similar distances, was proposed to span an immense scale, with estimated dimensions approaching 10 billion light-years. That number lands with a dull thud in the mind. 10 billion light-years is not just larger than the Sloan Great Wall. It is larger by almost an order of magnitude. It approaches a significant fraction of the observable universe itself. It is the kind of size that makes a cosmologist sit back and reread the paragraph, not because it is impossible to imagine, but because the implications are so strong. If a structure that large were confirmed as a coherent feature in the matter distribution, it would press hard against the expectation that the universe becomes statistically homogeneous on sufficiently large scales. It would not necessarily break the standard cosmological model outright because rare fluctuations can exist, but it would demand careful statistical accounting. It would raise the question of whether the structure is truly one connected overdensity, or whether it is a chance alignment of smaller features being interpreted as one larger wall. This is where the conversation becomes delicate, because the phrase Great Wall can smuggle certainty into a topic that actually requires caution. Unlike the Sloan Great Wall, which emerges from a systematic galaxy survey mapping millions of galaxy positions, the Hercules Corona Borealis Great Wall is inferred from a much smaller sample of events. Gamma-ray bursts are rare. Not every burst has a measured redshift. Not every burst has a clearly identified host galaxy. The sky coverage is uneven. Detection sensitivity varies. Follow-up observations do not happen uniformly across the sky. All of these factors create selection effects, patterns in the data caused by how the data is collected rather than by how the universe is arranged. Selection effects are not a minor technicality. They can create apparent clusters where none exist, or hide real clusters that do. If a region of the sky is observed more thoroughly, more bursts will be found there. If redshifts are easier to measure in certain regions due to observational scheduling, telescope access, or the brightness of afterglows, then those regions will appear more populated in a three-dimensional map, even if the underlying distribution is uniform. This is why the Hercules Corona Borealis Great Wall is often described as controversial. The claim is not that gamma-ray bursts are useless tracers. The claim is that the dataset is thin enough and the observational bias is complex enough that extraordinary scale requires extraordinary statistical care. Another complicating factor is the nature of gamma-ray bursts themselves. They are not a simple random sample of all galaxies. Long gamma-ray bursts are more common in certain environments, often associated with low metallicity star-forming regions. Metallicity in astronomy refers to the abundance of elements heavier than hydrogen and helium. In galaxies with fewer heavy elements, massive stars may retain more angular momentum, which can influence how collapses form. This means the gamma-ray burst rate can vary with galaxy type, star formation history, and cosmic epoch. The bursts are tracers, but they are biased tracers, and that bias can imprint patterns onto their distribution. Even if the underlying galaxy distribution were perfectly known, the distribution of bursts might not match it exactly. Some regions might produce more bursts per galaxy. Other regions might produce fewer. Over extremely large scales, these biases may average out, but in a sparse dataset, they can matter. So what does it mean, physically, if a clustering of gamma-ray bursts appears to suggest a structure spanning 10 billion light-years? The first answer is that it might be real in a statistical sense, a rare overdense region in the cosmic web. In the standard picture, the early universe contained tiny density fluctuations. Gravity amplified those fluctuations. The result is a web with a distribution of structure sizes. Most structures are modest, some are large, a few are extreme. If the Hercules Corona Borealis feature is real, it could represent one of these extremes, a large-scale ridge in the density field. The second answer is that it might be an artifact of limited sampling and selection bias. A sparse tracer can produce apparent clusters. A small number of points can, by chance, land closer together than average. And if the data collection process is uneven, that chance clustering can be reinforced. The third answer is that the feature might be a combination of multiple smaller, overdense regions that are not truly connected, but appear connected given the limited resolution of the tracer. In a dense galaxy survey, one might see that what looked like one wall is actually several walls aligned along a line of sight, or several adjacent filaments that are close, but not truly part of one coherent structure. With gamma-ray bursts, that kind of decomposition is harder. This is why when cosmologists discuss such claims, they often shift from the language of objects to the language of statistics. The question becomes not only what is the size of the structure, but what is the probability of observing such a clustering under a given cosmological model, and given the known selection biases of the dataset. The key point is that even if the Hercules Corona Borealis Great Wall exists as an overdensity, it is not a gravitationally bound object. At a scale approaching 10 billion light-years, cosmic expansion dominates. There is no single gravitational basin holding that entire region together. Any boundness would exist only in smaller subregions, like clusters embedded within the larger pattern. The wall, in that sense, would be a feature of the cosmic web rather than a single, cohesive thing. And that brings the story back to definition. If the largest thing means largest gravitationally bound object, then neither the Sloan Great Wall nor the Hercules Corona Borealis Great Wall qualifies. They are too large to be bound as single units. Their components may be bound locally, but the whole is not. If the largest thing means the largest identifiable structure in the distribution of matter, then the conversation becomes more open. A wall inferred from gamma-ray bursts could, in principle, represent an enormous overdensity. But for that claim to become widely accepted, it must survive the hardest part of cosmology, the part where the universe is measured not by what looks impressive, but by what remains after statistical scrutiny. There is a quiet lesson here about how cosmology handles extremes. The universe is full of dramatic phenomena, but cosmology is a discipline that forces drama to earn its credibility. It does not ask whether a claim is exciting. It asks whether the data supports it, whether the method is robust, and whether the result is consistent with everything else that has already been measured. The Hercules Corona Borealis Great Wall sits in that exact tension. It is an idea at the boundary, where the scale is so large that it pushes against expectations, yet the data is sparse enough that skepticism is scientifically healthy. It remains one of the most extreme proposed structures in modern astronomy, and it remains a reminder that when mapping the universe at the largest scales, the biggest enemy is not the darkness of space, but the thinness of the sample. And yet, even the controversy is useful. It forces the question to become sharper. If a structure of this scale can even be proposed, then the next step in the journey is not to chase larger and larger walls blindly. The next step is to ask what the standard cosmological model actually predicts about the maximum meaningful scale of structure and how that prediction is tested. In other words, after seeing the most extreme candidates, the mind naturally wants a stabilizer, a principle, a set of rules that says calmly and clearly how large structure can get before the universe becomes smooth. That is where theory steps in, not to replace observation, but to interpret it. And it begins with a deceptively simple idea that if you zoom out far enough, the universe should stop looking like a web of walls and voids and start looking, on average, almost uniform. After confronting structures with names like Great Wall, the mind naturally wants something firm to stand on. Not another image, not another dot map, but a rule that tells whether the universe is allowed to look like this at all. Cosmology has such a rule, and it is so quiet and so foundational that it can be easy to miss how much work it does. It is called the cosmological principle. The cosmological principle states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means that matter, when averaged over large enough volumes, has roughly the same density everywhere. Isotropic means that the universe looks the same in every direction, again when considered on large enough scales. This is not a claim that every region is identical. It is a claim about averages and about scale. It says that if an observer zooms out far enough, the lumpy web of galaxies and voids fades into something close to smooth. This principle matters because it is the starting assumption behind the most successful large-scale model of the universe. When Albert Einstein developed general relativity in 1915, he gave physics a new language for gravity. Gravity was no longer a force that acted across space like an invisible rope. It was the curvature of space-time itself, shaped by mass and energy. Soon after, Alexander Friedmann and Georges Lemaitre applied Einstein's equations to the universe as a whole. Under the assumptions of homogeneity and isotropy, those equations yield a family of expanding universe solutions. These solutions are the foundation of modern Big Bang cosmology. So the cosmological principle is not just an observational claim, it is a structural pillar. Without it, the simplest models of cosmic expansion become far more complicated. With it, the universe can be described by a small set of parameters: how fast it expands, what it is made of, and how its expansion changes over time. But an assumption is only valuable if nature cooperates. The universe could have turned out to be wildly uneven on the largest scales. It could have had a preferred direction. It could have had enormous gradients that never smooth out. So cosmology has spent decades testing whether homogeneity and isotropy are true in practice. One of the strongest tests comes from the cosmic microwave background radiation. This radiation is a relic from the early universe, released when the universe cooled enough for electrons and protons to combine into neutral hydrogen, allowing light to travel freely. That happened roughly 380,000 years after the Big Bang. When Arno Penzias and Robert Wilson detected this radiation in 1965, it provided direct evidence that the universe had once been hot and dense. Later missions such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite mapped this radiation across the entire sky. The Planck mission, operated by the European Space Agency, showed that the cosmic microwave background is remarkably uniform. The temperature variations are tiny, only a few parts in 100,000 relative to the mean. These anisotropies are the seeds of all later structure, but their smallness is the key point. A universe that began with variations that small will not naturally produce a present-day universe where density variations remain extreme on arbitrarily large scales. Gravity amplifies differences, but it has had a finite amount of time to do so, and the expansion of space works against unlimited growth. This is why structures like the Sloan Great Wall and the proposed Hercules Corona Borealis Great Wall attract scrutiny. The issue is not whether large structures exist. The issue is whether their size and frequency are consistent with a universe that is statistically homogeneous at large scales and seeded by small, early fluctuations. To address that question, cosmologists do not rely on the human eye alone. The human eye is excellent at seeing patterns, but it is not trained in probability. It will see a wall even when a wall is just a long ridge in a noisy landscape. So cosmology uses statistics to decide whether a feature is significant. One of the most important tools is the two-point correlation function. The idea behind it is simple. Take a large catalogue of galaxies and measure the probability of finding a pair of galaxies separated by a certain distance. Then compare that probability to what would be expected if galaxies were distributed randomly with the same average number density. If the probability is higher than random at small separations, that indicates clustering. If the probability approaches random at large separations, that indicates statistical homogeneity. In practice, the two-point correlation function shows strong clustering at small distances. Galaxies tend to gather because they form in the same dark matter structures and because gravity pulls matter together. As the separation increases, the excess clustering declines. Beyond a certain scale, the correlation approaches zero, meaning galaxy positions are no longer strongly related to one another, at that distance. This scale is sometimes described as the scale of homogeneity, though in detail the transition is gradual rather than abrupt. This is the first stabilizing lesson. The universe is lumpy, but the lumpiness has a characteristic range. Below that range, structure is obvious. Above that range, the universe begins to look smooth in a statistical sense. Another closely related tool is the power spectrum. If the correlation function describes clustering in real space, the power spectrum describes clustering in Fourier space as a function of scale. The power spectrum is especially useful because many theoretical predictions, including predictions from inflation, are naturally expressed in terms of how fluctuations behave across different wavelengths. Observations of the cosmic microwave background give a direct measurement of the early universe power spectrum. Galaxy surveys give a measurement of the later universe power spectrum. Comparing the two is a way of testing the entire story of structure formation. A particularly important feature in the galaxy power spectrum is the imprint of baryon acoustic oscillations. In the early universe before atoms formed, matter and radiation were tightly coupled in a hot plasma. Pressure waves traveled through this plasma, creating oscillations in density. When photons decoupled at recombination, those oscillations left a faint preferred scale in the distribution of matter. Today, that scale appears as a slight bump in the galaxy correlation function, a standard ruler used to measure cosmic expansion. Large surveys such as the Sloan Digital Sky Survey have detected this feature, and it supports the standard cosmological model with impressive consistency. So the universe is not just smooth or lumpy, it is lumpy in a particular, measurable way. Its fluctuations have a spectrum, a statistical signature that links the early universe to the present. This statistical signature is a more reliable guide than any single dramatic structure that happens to catch attention. This is also where cosmic variance becomes important. Cosmic variance is the idea that because there is only one universe to observe, and because observers occupy only one vantage point within it, measurements of large-scale properties have an unavoidable statistical uncertainty. If an observer measured the universe from a different location, the largest structures visible in that direction might look slightly different. This does not mean the universe changes, but it means any measurement of large-scale patterns is drawn from a finite sample. Even the best surveys map only a portion of the observable universe. And even the observable universe is only a portion of whatever exists beyond the horizon. Cosmic variance matters most at the larger scales, where the number of independent regions is small. It is easier to estimate an average density on small scales, because there are many small regions to sample. It is harder to estimate an average on the larger scales, because there are fewer independent volumes. This is one reason why the largest claimed structures demand careful treatment. A rare fluctuation might appear more extreme simply because the sample is limited. Selection effects add another layer. A galaxy survey does not detect every galaxy uniformly across space. Distant galaxies are dimmer and harder to observe. Dust in the Milky Way blocks parts of the sky. Instrument sensitivity varies. Spectroscopic follow-up is not uniform. Gamma-ray burst samples are even more sensitive to selection effects because detection depends on burst brightness, sky coverage, and follow-up success. A structure inferred from a biased sample can look more dramatic than the underlying matter distribution actually is. So cosmology relies on careful survey calibration, completeness corrections, and mock catalogues generated from simulations. The purpose of a mock catalogue is to create a synthetic universe consistent with the standard model, then apply the same selection effects as the real survey and see what kinds of apparent structures emerge. If the mock catalogues often produce features similar in size and shape to the observed feature, then the observed feature is likely consistent with the model. If the observed feature is far more extreme than what mocks produce, then either the model is incomplete or the feature is misinterpreted. This is where the interpretation of Great Walls becomes more grounded. The Sloan Great Wall is enormous, but when compared against simulations and statistical expectations, it can be understood as an extreme but not impossible feature in a cosmic web generated by the lambda cold dark matter model. The Hercules Corona Borealis claim, because it relies on a sparser tracer, is harder to evaluate, and that is why it remains debated. The debate is not merely about whether it exists, but about whether the dataset and methods are sufficient to claim a structure of that scale with confidence. Now, the cosmological principle can be stated more carefully in the language of modern cosmology. It does not say that the universe is smooth everywhere. It says that the universe is statistically homogeneous and isotropic above a certain scale. That distinction is crucial. Statistical homogeneity allows for fluctuations. It even allows for rare, large fluctuations. What it does not allow is a persistent trend, like a universe that is significantly denser in one direction than another on the largest scales, or a universe where structure never averages out no matter how large the volume becomes. So the question becomes practical. What is the scale where averaging makes the universe look smooth? Different analyses produce slightly different values depending on a method and dataset. But the general conclusion is that homogeneity emerges on scales of several 100 million light-years, and certainly by around 1 billion light-years when sufficiently large volumes are considered. This is not an absolute boundary. It is a transition zone, but it is enough to say that a structure spanning many billions of light-years would be unusual and would require strong evidence and careful statistical justification. This is where a common misunderstanding can quietly sabotage the conversation. Homogeneity does not mean there cannot be a long structure 1 billion light-years long. It means that if an observer averages matter density over volumes larger than the homogeneity scale, the average approaches a constant value. A long ridge can exist within a landscape that is still, on average, flat. It is the difference between local terrain and global statistics. Another subtlety is how structure is defined in the first place. If a structure is defined as a connected region above a certain density threshold, then changing the threshold changes the structure. Raise the threshold and the structure breaks into smaller pieces. Lower the threshold and separate structures may merge into one continuous region. There is no single perfect threshold chosen by nature. Cosmologists choose thresholds that are physically motivated and statistically useful, but those choices influence what is labeled as one structure versus many. This is another reason why the term largest structure must be handled with care. The size depends on the definition. This does not mean the concept is meaningless. It means it is conditional. And conditional answers can still be honest, as long as the conditions are stated plainly. At this stage, the role of the cosmological principle becomes clearer. It is not a rule that forbids the cosmic web. It is a rule that tells how the web behaves when you zoom out far enough. The web is real. Filaments and voids are real. Great walls may be real as extended overdensities, but the web does not keep forming larger and larger coherent features forever. It has a statistical character that limits how extreme its largest features can be. The principle also aligns with another major feature of modern cosmology, the idea that the universe has no preferred center or preferred direction. Isotropy implies there is no special direction in which the universe is fundamentally different. Observations support this to high precision through the near uniformity of the cosmic microwave background. There are small anomalies debated in the literature, but the broad picture remains that the universe is isotropic to an extraordinary degree. It is worth pausing on how strange this is, in a gentle way. Human experience is built in a world where direction matters. Up and down matter. North and south matter. Coastlines shape cultures. The universe, on its largest scales, does not care about such distinctions. It is lumpy locally, but it is astonishingly impartial globally. And now the original question can be reframed with more discipline. The largest thing in the universe cannot be decided solely by pointing to a long filament or a large overdensity. It must be decided by choosing a definition and then testing whether the candidate fits within the statistical framework of cosmology. If the definition is gravitational binding, the answer will favor clusters because binding is a physical condition. If the definition is the largest overdense region in the cosmic web, the answer will involve statistical definitions and surveys. If the definition is the largest region that can be described at all, then the observable universe enters, and that is a different kind of boundary, one defined by light travel time and cosmic expansion rather than by density thresholds. For now, the cosmological principle and its statistical machinery serve as the stabilizer. They tell what it means for a structure to be meaningful, and they explain why some claimed structures require skepticism. They show that the universe is structured, but structured within limits. With this framework in place, the next step becomes less about chasing bigger names and more about understanding horizons. Because even if a structure could be traced across a huge region, there is a deeper limit that no survey can escape. There is a distance beyond which no light has had time to reach here. And that horizon defines the largest region that can ever be mapped from this vantage point, no matter how clever the instruments become. There is a limit to every map, not because the cartographer is lazy, but because reality refuses to provide more paper. Even the most ambitious sky survey, even the most sensitive telescope, even the most patient accumulation of data runs into the same boundary. Light has only had so long to travel. The universe has only been expanding for so much time. And because of that, there is a largest region that can ever be observed from here. That region is called the observable universe. At first, the phrase sounds like a simple, practical label. It is the part of the universe that can be seen. But in cosmology, it carries a more specific meaning. The observable universe is the region of space from which light has had time to reach Earth since the beginning of cosmic expansion. It is defined by a horizon, not by a physical edge. It is not a wall, not a boundary made of matter, and not a shell. It is a limit set by time and by the speed of light. This immediately creates a strange candidate for the title of largest thing. Because if the question is interpreted broadly as what is the largest region that can be meaningfully defined at all, the observable universe becomes an answer. It has a size. It can be estimated. Its contents can be described. It is, in a certain sense, the biggest named structure in the whole conversation. But it is a very different kind of thing than a galaxy cluster. A galaxy cluster is held together by gravity. Its members are bound. If cosmic expansion continues forever, a rich cluster remains a single coherent unit. The observable universe is not like that. It is not bound. It is not held together by anything in the ordinary sense. It is simply the portion of space-time that is causally connected to us through the travel of light. The size of the observable universe is larger than people often expect on first encounter. The universe is about 13.8 billion years old, and it might seem natural to assume that the observable universe should therefore have a radius of about 13.8 billion light-years. But the real number is larger. The reason is that while light has been traveling, space itself has been expanding. The light has crossed a changing landscape. It has traveled through a universe that kept stretching while it moved. The result is that the present-day radius of the observable universe is roughly 46 billion light-years. That gives a present-day diameter of about 93 billion light-years. This is not because light traveled faster than the speed of light. It is because the distance between where the light started and where it ended grew during the journey. This number is not an arbitrary headline figure. It is a consequence of the expansion history of the universe, which is encoded in cosmological parameters measured by observations. Those parameters are constrained by the cosmic microwave background, by baryon acoustic oscillations, and by supernova distance measurements. Different parameter values can shift the exact size slightly, but the broad scale is stable. The observable universe is vastly larger than the simple age-time speed of light intuition suggests. So if someone insists on the largest definable region, the observable universe is a natural answer. It is the largest region that can be mapped in principle, and it contains all the named structures discussed so far. The Sloan Great Wall sits inside it like a ridge on a continent. The proposed Hercules Corona Borealis Great Wall, whether it holds up or not, would also sit inside it. The entire cosmic web, as traced by galaxies and clusters, is an internal pattern within this horizon-defined volume. Yet calling the observable universe a thing still feels odd because it is defined by perspective. Another observer in a galaxy billions of light-years away has their own observable universe centered on their location. Much of it would overlap with ours, but not all. There is no single observable universe for all observers. There are many, each centered on a vantage point. The phrase, the observable universe, really means the observable universe from here. That perspective dependence is not a flaw. It is part of what makes the concept physically meaningful. In relativity, information travels at finite speed. Causality has shape. Horizons are real features of space-time. They are as physically significant as any object, even if they are not made of matter. This is why cosmology often makes a careful distinction between the observable universe and the entire universe. The entire universe might be larger, possibly vastly larger, and it might even be infinite. But the entire universe cannot be observed in full. Only a region can be. That is the one we live inside. So the question becomes more precise again. Is the observable universe the largest thing, or Is it simply the largest region that can be talked about responsibly? If the goal is to understand the larger structures that form within the universe, the observable universe is the stage, not the actor. It is the boundary of observation, not the product of structure formation. The cosmic web is the actor. Clusters, filaments, voids, and overdensities are the architecture built within the stage. Still, the observable universe does something important for the original question. It tells you that there is a ceiling on claims. Any claim structure cannot meaningfully exceed the size of the observable universe, and any structure that approaches a significant fraction of it is immediately suspicious, not because it must be false, but because it presses against expectations of homogeneity and against the fact that structure formation has finite time to operate. It also tells you something about why the largest structure claims are hard to settle. The largest scales are where sampling becomes thin, where cosmic variance is strong, and where the distinction between an object and a statistical fluctuation becomes most fragile. A galaxy cluster is easy to define because it is bound and compact compared to cosmic distances. A billion light-year wall is harder. A 10 billion light-year wall is harder still. And when a claim begins to approach the size of the observable universe, it begins to compete with the idea that the universe is smooth on the largest scales. So the horizon is a conceptual turning point. It sets the outer limit, but it also invites another question that is quietly more unsettling. If the observable universe is so large today, and if the universe has been expanding all this time, then what was the universe like before the structures formed? What did it look like when it was young, smooth and hot? And what mechanism produced the tiny initial irregularities that gravity later amplified into the cosmic web? To answer that, the story has to move backward beyond galaxies, beyond clusters, beyond even atoms, toward an era when the universe was far simpler and far stranger. In that early time, matter was not arranged into stars and galaxies. It was a hot, dense plasma. Photons scattered constantly from free electrons. Space was filled with radiation and particles so tightly coupled that the universe behaved like an opaque fog. Tiny fluctuations existed, but they were not yet the web. They were only the faintest hints of future structure. The lead-in explanation for why the universe began so smooth and for why it contains the specific pattern of tiny fluctuations observed in the cosmic microwave background, is a process called cosmic inflation. Inflation was proposed in the early 1980s, most famously by Alan Guth, as a way to solve several puzzles in Big Bang cosmology. One puzzle is the horizon problem. The cosmic microwave background is nearly the same temperature in all directions, even in regions that, under a naive Big Bang expansion, would not have been in causal contact early enough to equalize their temperature. Another puzzle is the flatness problem. The geometry of the universe appears very close to spatially flat, and maintaining that flatness in standard expansion requires finely tuned initial conditions. Inflation addresses both problems by proposing that the universe underwent a brief period of extremely rapid expansion very early on, stretching space by an enormous factor. The key idea is not that galaxies flew apart faster than light. The key idea is that space itself expanded. In general relativity, there is no prohibition on space expanding in such a way that the distance between 2 points increases faster than the speed of light. This does not violate relativity, because no object locally travels through space faster than light. Instead, the metric describing space changes. During inflation, a very small, causally connected region could have been stretched into a region large enough to contain the entire observable universe today. That means the smoothness of the cosmic microwave background does not require the entire sky to have been in contact in the ordinary way at the time the microwave background was released. It only requires that the region that later became our observable universe was once small enough to equilibrate before inflation stretched it. Inflation also provides a natural mechanism for the origin of structure. Quantum mechanics says that fields fluctuate. Even in a vacuum, quantum fields have unavoidable uncertainties. During inflation, these tiny quantum fluctuations were stretched to astronomical scales. When inflation ended, those fluctuations became frozen as slight variations in density and gravitational potential across space. These variations were tiny. They were not cliffs. They were gentle ripples. But gravity is a patient amplifier. Over billions of years, those slight differences grew into the cosmic web. The reason this story is so compelling is that it connects three very different things. It connects quantum physics, which governs the smallest scales. It connects general relativity, which governs space-time and gravity. And it connects the largest observed structures, which trace the history of gravitational growth. A small quantum fluctuation, stretched by inflation, becomes a slight density difference in the early universe. That density difference becomes a slightly denser region of dark matter. That dark matter region attracts more matter. Over time, it becomes a halo. Halos merge into larger halos. Gas falls in, cools and forms stars. Stars gather into galaxies. Galaxies gather into clusters. Clusters connect through filaments, and the web emerges. This chain is one of the great narrative arcs of modern cosmology. And it is not merely storytelling, it is tested. The cosmic microwave background provides the strongest early test. Its temperature anisotropies reflect the density fluctuations present when the universe was about 380,000 years old. The pattern of those anisotropies has specific statistical properties. It has a power spectrum with peaks and troughs that reflect sound waves in the early plasma, known as acoustic oscillations. The details of those peaks encode the composition of the universe, including how much ordinary matter exists, how much dark matter exists, and how the geometry of space behaves. The Planck satellite mapped these anisotropies with extraordinary precision. Its results strongly support a universe whose early fluctuations are very close to Gaussian, meaning they behave like a random field with a specific statistical distribution, and whose spectrum is close to scale invariant, meaning fluctuations have nearly the same amplitude across a wide range of scales. These are key predictions of simple inflationary models. The match is not perfect in every detail, and there is ongoing research into inflation's exact mechanism, but the broad agreement is one of the major successes of modern cosmology. Once those initial fluctuations are known, cosmologists can simulate structure formation forward in time. They can start with a universe that has tiny density ripples, consistent with the cosmic microwave background, then allow gravity to operate. In the standard picture, cold, dark matter collapses first, forming halos and filaments. Ordinary matter follows, cooling and forming stars and galaxies. When these simulations are done at large scale with enough resolution, they produce a cosmic web that resembles what is observed in galaxy surveys. The Millennium Simulation, associated with researchers at the Max Planck Institute for Astrophysics, is one famous example of this approach. The point of mentioning it is not to crown a single simulation as definitive, but to illustrate that the web is not a surprise. It is what gravity does to small fluctuations when given time. Inflation also implies something else that changes how the largest thing question feels. If inflation happened, then the observable universe might be a small patch of a much larger universe. The region outside our horizon may contain more cosmic web, more galaxies, more clusters, and perhaps variations on scales we cannot see. Some inflationary ideas even suggest that inflation could occur in a way that produces regions with different physical properties, a concept sometimes called eternal inflation. But these ideas move toward the edge of what can be tested. They are not established facts in the way the cosmic microwave background is established. They are possibilities suggested by some models. The honest boundary is that observations can only constrain what lies within or near our horizon. Beyond that, cosmology becomes careful. It can propose models, explore their consequences, and check whether they are consistent with what is observed. But it cannot simply declare what exists beyond the horizon with the same confidence. This matters for the question of the largest thing, because it reminds you that the largest structures discussed so far are the largest structures within the observable universe. There may be larger structures beyond, but if they are beyond the horizon, they cannot be identified from here. They cannot be mapped. They cannot be confirmed. They do not belong in a list of known objects. So there are now two different senses of largest. There is the largest thing that can be observed and described within the horizon, and there is the largest thing that might exist in a larger cosmos that may extend beyond our horizon. The first belongs to science, with strong evidence. The second belongs to scientific speculation constrained by evidence. For the purposes of this journey, the strongest footing remains with what can be observed and tested. Within the observable universe, the largest gravitationally bound things are galaxy clusters. The largest identifiable patterns are features of the cosmic web, including structures like the Sloan Great Wall and the debated Hercules Corona Borealis feature. The observable universe itself is the largest region that can be defined from here, but it is not a bound object. It is a horizon defined by causality. Inflation helps unify these categories because it explains why there is a horizon, why the universe is so uniform at the largest scales, and why the initial seeds of structure were tiny and statistical rather than wild and chaotic. Inflation sets the initial conditions that allow a meaningful scale of homogeneity to emerge later. Without something like inflation, the early smoothness and the statistical properties of the cosmic microwave background become much harder to explain. There is also a quiet philosophical twist that inflation encourages without requiring any drama. If the larger structures began as quantum fluctuations, then the biggest architecture in the universe is ultimately rooted in the smallest uncertainties. That does not mean the universe is fragile. It means the universe is coherent. Small physical rules scale up in time and space to produce enormous outcomes. And it means that when searching for the largest thing, it is worth remembering that the universe does not build from the top down. It builds from the bottom up. It starts nearly smooth with tiny ripples. Gravity amplifies. Expansion stretches. Dark matter scaffolds. Ordinary matter lights the structure up with stars. The observable universe is the limit of what can be seen from here. But the origin of what is seen lies in that early smooth plasma, in the tiny fluctuations mapped in the cosmic microwave background, and in the inflationary stretch that set the stage for everything that followed. With that origin story in place, the next question becomes almost inevitable. If inflation seeded structure and the observable universe sets the horizon, then what determines how far structure can grow before it stops making sense? Gravity can build, but expansion can tear apart. And in the modern universe, expansion is not merely continuing, it is accelerating. Which means the largest structures are not just limited by the past, they are limited by the future. By the time the universe had assembled its first galaxies, gravity still had the advantage. Matter was denser. Distances between growing structures were smaller. The cosmic web could thicken. Clusters could build. Filaments could funnel gas and dark matter into nodes. In that earlier era, the universe was like a workshop where the raw material was close enough for gravity to reach it. But the universe does not only build, it also stretches. Cosmic expansion is not a background detail, it is the stage motion under everything else. Over time, as space expands, matter becomes more dilute. Gravity still works, but it has less to work with per unit volume. And then, in the late 1990s, something even stranger became clear. Expansion is not merely continuing, it is accelerating. That discovery came from a very specific kind of astronomical measurement. It did not begin with giant walls or deep galaxy maps. It began with objects that can be used as cosmic distance markers. Type 1a supernovae are a particular class of stellar explosion. They are not the death of a single massive star in the way core collapse supernovae are. Instead, they involve a white dwarf, the compact remnant of a sun-like star in a binary system. When a white dwarf accretes matter from a companion or merges with another white dwarf, it can reach conditions that trigger a thermonuclear runaway. The white dwarf is disrupted in an enormous explosion that produces a relatively consistent peak brightness, with variations that can be standardized using observed light curve shapes. That standardization is what makes Type 1 a supernovae useful. If the intrinsic brightness is known, the observed brightness reveals distance. By comparing distance with redshift, astronomers can infer how the expansion rate has changed over time. Two teams carried out the key work in the 1990s. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt, with Adam Rees playing a major role. They observed distant Type 1 as supernovae and found that these supernovae were dimmer than expected in a universe where expansion was slowing down under gravity alone. The simplest interpretation was that the expansion of the universe has been speeding up for the last several billion years. This acceleration is commonly attributed to dark energy. Dark energy is not directly observed in the way stars are observed. It is inferred from its effect on the expansion history of the universe. In the simplest form, dark energy behaves like a cosmological constant, a constant energy density associated with empty space itself. In the lambda cold dark matter model, lambda represents this dark energy component, and cold dark matter represents the dominant clustering matter component. The combination is powerful. Cold dark matter builds structure by gravity. dark energy stretches space faster and faster, making it harder for gravity to gather matter across very large distances. The universe becomes a kind of tug of war, but not a symmetrical one. Gravity wins locally where density is high. Dark energy dominates globally as the overall expansion accelerates. This has direct consequences for the largest structures. It means the universe is not endlessly patient. There is a window of cosmic history when large-scale structure formation is efficient. Early on, matter dominates, so structures grow rapidly. Later, dark energy dominates, so growth slows. This can be described with a simple idea that stays voiceover friendly. In the early universe, the average matter density was high, so gravity could pull matter together efficiently. As the universe expanded, matter density dropped because the same mass was spread through a larger volume. Dark energy, if it behaves like a cosmological constant, does not dilute in the same way. Its density remains nearly constant as space expands. That means that as time goes on, dark energy becomes more important relative to matter. Once dark energy dominates, the large-scale expansion accelerates. Structures that are already gravitationally bound remain bound. Structures that are not bound are pulled apart more rapidly, and structures that are only loosely held together at the edges begin to fracture into smaller bound islands. This is why superclusters sit on a boundary. A rich cluster is a deep gravitational well. A supercluster is more like a chain of wells embedded in a broader, overdense region. Some parts will remain together. Some parts will not. The cosmic web remains a pattern, but its long-range connections become less effective at feeding growth into new, ever larger systems. The most important point for the original question is that dark energy enforces an upper limit on what can become a single, bound thing. Gravity can only bind what it can hold against the expansion. When expansion accelerates, the largest bound systems become clearer because the universe itself begins to sort structures into what survives and what stretches apart. So what survives? The answer is the largest gravitationally bound structures, and those are galaxy clusters. Not walls, not superclusters as unified wholes, not the cosmic web as a complete connected network. Clusters. A galaxy cluster is a system in which gravity holds together galaxies, hot gas, and dark matter in a single shared gravitational potential. Clusters are not just dense in a casual sense, they are bound in a dynamic sense. If the member galaxies are moving at speeds that would otherwise carry them away, the fact that they remain indicates the gravitational well is deep enough to keep them trapped. Clusters reveal their mass in multiple independent ways. One way is through the velocities of galaxies within them. A galaxy cluster often has internal velocity dispersions on the order of 1,000 kilometers per second. Those speeds are large, and they are not gentle orbital velocities like planets around a star. They are chaotic, multi-directional motions within a vast gravitational environment. If the cluster had only the mass in visible galaxies, those motions would be too fast, and the cluster would disperse. The fact that it remains bound implies far more mass, overwhelmingly in dark matter. Another way clusters reveal mass is through gravitational lensing. According to general relativity, mass curves space-time and bends light. In cluster lensing, background galaxies are distorted into arcs and stretched shapes. Strong lensing can produce dramatic arcs and even multiple images of the same background galaxy. Weak lensing produces subtler distortions, measurable statistically across large numbers of background galaxies. These lensing patterns allow astronomers to reconstruct the cluster's mass distribution, showing that most of the mass is invisible. A third way clusters reveal mass is through the hot intracluster medium, the plasma filling the space between galaxies. This gas is heated to tens of millions of degrees by the gravitational potential and by shocks from merging subclusters. At those temperatures, the gas emits X-rays, which have been mapped by instruments such as NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton. The brightness and temperature structure of the X-ray emission provides another window into the cluster's mass and dynamical history. And then there is an especially striking case that links these ideas together in a way that is hard to ignore. The Bullet Cluster is a famous example of a cluster collision. Two galaxy clusters pass through each other. The hot gas, which interacts electromagnetically, experienced drag and slowed, piling up in between. The galaxies, which are mostly empty space separated by vast distances, pass through more easily. Gravitational lensing maps showed that most of the mass associated with dark matter traveled with the galaxies rather than with the gas. This separation between the bulk of mass and the bulk of ordinary matter is considered strong evidence for the existence of dark matter as a component distinct from hot gas. It is one of the clearest demonstrations that clusters are not only large, but that their binding framework is dominated by something unseen. All of this makes clusters exceptionally good candidates for the largest thing in the strict gravitational sense. They are physically coherent. Their boundaries can be defined in practical ways, such as the radius within which the average density exceeds the cosmic average by a particular factor. Their mass can be measured through multiple methods that agree broadly. Their long-term fate is to remain bound even in an accelerating universe. But clusters still vary. Some are modest, some are monsters. The richest clusters contain thousands of galaxies and have masses that can reach several quadrillion times the mass of the Sun. They can span several million light-years. Their dark matter halos extend beyond the visible galaxy distribution. Their hot gas forms a vast luminous atmosphere in X-rays. They grow by merging with other clusters and by accreting galaxy groups along the filaments of the cosmic web. Yet even the largest clusters are not the end of structure. They are the end of bound structure on the largest scale. They are the final islands that remain unified as the universe continues to accelerate. This is where the original question becomes clearer again. When the phrase largest thing is interpreted in the most physically concrete way, as largest long-lived bound object, then the universe gives a fairly stable answer: massive galaxy clusters. The next question becomes how this answer compares to the more dramatic named walls. The Sloan Great Wall is a vast overdensity traced by galaxies and clusters. It is real in the sense that the galaxy distribution shows an extended feature, but it is not one gravitational system. Its clusters are bound, but the wall as a whole is not bound. It is a long ridge in the cosmic web. The proposed Hercules Corona Borealis Great Wall, if it represents a genuine overdensity, will be even more clearly unbound as a whole. Its scale is too large for gravity to hold together in a single basin under the standard expansion history. Any cohesion would exist only in smaller embedded regions like clusters and groups, while the broader pattern would be statistical. Dark energy does not make those walls irrelevant. It clarifies what they are. It says calmly that the largest patterns in the galaxy distribution are not the same thing as the largest gravitationally bound entities. Walls can be real patterns, and clusters can be real objects, and the universe can contain both at once. There is another consequence of dark energy that is worth stating plainly, because it reshapes the meaning of the largest structures over time. In a universe where expansion accelerates, there is a horizon beyond which events happening now will never be able to influence an observer here. This concept is called the cosmic event horizon. It is different from the particle horizon, which defines how far light has traveled to reach an observer since the early universe. The event horizon defines the limit of future causal contact. Even if light is emitted now, if it is far enough away, the accelerating expansion can prevent that light from ever reaching here. Over very long timescales, this means the observable universe will not remain a window into ever more distant regions. Instead, distant galaxies will recede so rapidly that their light will never reach here in the far future. Even if emitted, the local gravitationally bound region will remain, and beyond it, the universe will fade away observationally. This gives a quiet, almost unsettling twist to the question. The largest thing that can be seen depends on when the question is asked. In the far future, observers in a bound cluster might see only their local cluster and perhaps a few nearby companions. The broader cosmic web and distant clusters would be beyond the event horizon, no longer observable. In that future, the largest thing would not merely be the largest bound thing. It would also be the largest visible thing. But in the present era, it is still possible to see deep into cosmic history. The cosmic microwave background remains visible as the afterglow of the early universe. Distant galaxies can still be observed, great walls and filaments can still be mapped, at least in the statistical sense. So the universe is being viewed during a kind of fortunate epoch, one where both the products of structure formation and the evidence of the early universe remain accessible. The question, what is the largest thing, is being asked at a time when the cosmos still allows a wide view. Now there is a subtle but important clarification to make about the word largest in the gravitational sense. A galaxy cluster is large by mass and by spatial extent. But clusters also have a characteristic scale where gravity dominates. That scale can be expressed in terms of a boundary where the cluster's internal gravitational attraction overcomes the expansion. Inside that boundary, matter remains bound. Outside it, expansion dominates and matter is less likely to remain attached. This boundary is not a physical shell. It is a useful conceptual marker. It helps define what part of a cluster is truly part of the cluster in a dynamic sense. In practice, astronomers often define cluster radii using density thresholds relative to the critical density of the universe, which itself depends on the expansion rate. These definitions are technical, but the intuitive meaning is simple. A cluster can be defined as the region where matter is concentrated enough that gravity keeps the system together. And in an accelerating universe, that definition becomes more stable over time. There is less new, large-scale growth, so clusters become increasingly isolated and increasingly well-defined as the largest bound units. This is also why superclusters fade as candidates for largest bound thing. A supercluster is a large, overdense region containing many clusters but its outskirts are not necessarily bound. Over time, the parts that are not bound drift away. The supercluster fractures into separate clusters and smaller bound groups. The name remains useful for describing the present-day arrangement, but it does not describe a single long-term object. So the acceleration of expansion acts like a cosmic sorting mechanism. It does not destroy clusters, it preserves them. It does not preserve superclusters as unified entities. It does not preserve filaments as permanent bridges between distant clusters. It does not preserve the cosmic web as a connected network forever. It preserves the deepest gravitational basins and allows the rest to stretch. In this way, dark energy does something that feels almost like an editorial decision made by physics itself. It decides which structures will have a future as coherent things and which will become historical patterns that slowly dissolve. There is also a gentle point about scale that helps keep the story grounded. The largest structures being discussed, walls spanning billions of light years, are enormous in spatial extent, but not necessarily enormous in density contrast. On those scales, the density differences between an overdense ridge and the average background can be relatively modest. It is not like comparing a mountain to empty space. It is more like comparing a slightly thicker region of mist to a slightly thinner one, just spread over unimaginable distances. That is why statistical tools are so important, and why the cosmological principle remains compatible with the existence of large features. A large feature can exist without implying the universe is fundamentally inhomogeneous, as long as the feature represents a rare fluctuation rather than a persistent trend. A galaxy cluster, on the other hand, represents a strong local overdensity. The density of matter inside a cluster compared to the cosmic average is enormous. The cluster is a true concentration, a place where gravity has decisively beaten expansion on local scales. That is why clusters are the clearest answer to the strict definition. They are not merely large by arrangement, they are large by consolidation. So the question now has a form that can be answered cleanly, even if the full story remains rich. The largest bound things are massive galaxy clusters. They are the biggest coherent gravitational units the universe builds and keeps. Great walls and superclusters are among the largest identifiable patterns in the cosmic web, but they are not bound as single objects, and they will not remain unified forever in an accelerating universe. This does not make the walls less fascinating. It makes them more honest. It places them where they belong as extended statistical features, dramatic ridges in a vast terrain. And with that clarity comes the next step in the journey. If dark energy sets a limit on the growth of bound structures, and if homogeneity emerges on large scales, then there must be a scale where the very concept of structure changes character, where it becomes less like objects and more like fluctuations. That scale is not a single sharp line in space, but it is a real transition, and it is where the phrase, "At what point does structure stop making sense?" becomes the central question. Because beyond that scale, the universe does not offer a bigger thing. It offers a smoother universe. There is a moment in this story where the universe stops behaving like a museum of objects and starts behaving like a field of statistics. Not because anything physical snaps or breaks, but because the act of looking changes what can honestly be said. A galaxy cluster can be pointed to and weighed. A supercluster can be traced by the flow of galaxies. A great wall can be outlined by overdensities in a survey. But keep zooming out, keep widening the frame, and something subtle happens. The clusters become dots, the filaments become a texture, the voids become a faint mottling. The entire cosmic web, so dramatic up close, begins to fade into an average. That fading does not mean the web was an illusion. It means the web has a scale. Cosmology calls the transition the scale of homogeneity. It is the scale at which the universe, when averaged over sufficiently large volumes, approaches the same mean density everywhere. Below that scale, the universe is obviously structured. Above that scale, the universe is still structured locally, but the large-scale distribution becomes statistically smooth. Structure does not disappear. It stops growing in meaning. This is one of the most misunderstood ideas in popular discussions of largest structures, because it sounds like a claim that the universe becomes bland. It does not. It sounds like a claim that walls and filaments are forbidden. They are not. It is a claim about averaging and about probability. It is the difference between weather and climate. A storm can be violent and real. Climate can still have stable averages. A long filament can be real. The universe can still be homogeneous when considered broadly enough. To test homogeneity, cosmologists do not rely on a single image or a single catalogue. They use methods that are deliberately designed to avoid being fooled by one spectacular feature. One common approach is to take a large galaxy survey, choose many random centers, and count how many galaxies lie within spheres of increasing radius around each center. This is sometimes called the counts in spheres method. If the universe is homogeneous, the number of galaxies within a sphere should grow roughly with the volume of the sphere once the radius is large enough, allowing for the overall selection effects of the survey. In a fully uniform distribution, doubling the radius increases the volume by a factor of 8, and the counts should follow that scaling. In the real universe, on small scales, the counts do not scale like a smooth volume because galaxies cluster. On larger scales, the scaling begins to approach what homogeneity predicts. Another way of stating the same idea is through the correlation dimension. If galaxies were distributed like a fractal on all scales, the effective dimension measured by counts would remain below 3 even as radius grows. If the universe becomes homogeneous, the measured dimension approaches 3 at-large radii. In practice, analyses of major surveys indicate that the universe approaches this homogeneous behavior on scales of several 100 million light-years. The exact scale depends on the survey, the redshift range, and the statistical choices, but the broad conclusion remains stable. There is a transition zone, not an infinitely extending fractal hierarchy. This matters for the original question because it tells where largest structure stops being an object category and becomes a language category. Above the homogeneity scale, a structure can still be identified in the data, but its meaning becomes more dependent on how the definition is drawn. Lower the density threshold and separate features merge into one. Raise it and one feature fractures into many. On those scales, the boundaries are no longer carved by a single gravitational basin. They are carved by a choice. Even the word wall begins to sound different once this is understood. A wall on Earth is a barrier that separates one region from another. A great wall in cosmology is a region where the density is higher than average along an extended shape. It is not a barrier. It is not an edge. It is an over-density ridge within a field, that is becoming smooth in the large-scale statistical sense. This is why the cosmological principle survives the discovery of large features. The principle does not demand that every region is the same. It demands that if an observer averages over volumes large enough, the distribution approaches the same statistics everywhere and in every direction. A universe can contain rare, dramatic ridges and still be statistically homogeneous. The key is that those ridges do not dominate the average when the averaging volume is large enough, and that they are not accompanied by an overall gradient or preferred direction on the largest scales. It also explains why claims of extremely large structures attract so much attention. The larger the claimed structure, the closer it gets to the scales where homogeneity should be apparent. At that point, the question is no longer only, is this real? But also, what does real mean here? Is it an overdensity significant beyond selection effects and cosmic variance? Is it a coherent feature across space, or a patchwork of smaller structures aligned in a way that looks unified? Is it something a different observer elsewhere would also identify as a single connected feature? Or is it a feature of this particular vantage point and this particular dataset? Cosmic variance becomes a quiet antagonist at these scales. The observable universe is finite, and surveys are smaller than the observable universe. On the larger scales, the number of independent regions that can be sampled is limited. That means the measured largest features are partly a function of what is available to sample. A rare fluctuation can appear unusually prominent simply because there are not many independent opportunities for the averages to converge. This is not a failure of science. It is a property of being inside a universe rather than outside it. Selection effects too become more dangerous as scales grow. A survey is never perfectly uniform. Dust in the Milky Way reduces sensitivity near the galactic plane. Telescope time, observing strategy, and instrument design produce uneven coverage. Spectroscopic redshifts are harder for faint, distant galaxies. Photometric redshifts carry larger uncertainties. Gamma-ray burst catalogues are sparse and strongly shaped by detection and follow-up probability. At small scales, these issues can be corrected relatively well because there is plenty of data. At the larger scales, small biases can become large, apparent features. So the scale of homogeneity is not just a number, it is a guide for humility. It says that beyond a certain scale, the universe is best described statistically rather than with object language. It suggests that the most honest phrasing changes from "this is the biggest thing" to "this is one of the largest overdensities identified under a particular definition," in a universe that is otherwise statistically smooth at larger scales. That may sound less dramatic, but it is actually more interesting because it reveals what the largest structures really are. They are the extreme outcomes of a probabilistic beginning. The universe began with small fluctuations. Those fluctuations are measured in the cosmic microwave background, mapped in precision by missions such as the Planck satellite. Their statistical properties, including their near Gaussian character and their near-scale invariant spectrum, are consistent with inflationary ideas developed by scientists such as Alan Guth and André Linde. Those fluctuations evolved under gravity into a web of structure. The web contains extremes because probability distributions contain extremes. The universe is not obligated to produce only average outcomes. It is obligated to produce a distribution. So when a Great Wall is discussed, the most revealing question is not whether it exists in a map. The most revealing question is where it sits in the distribution. Is it rare but expected? Is it rare and borderline? Or is it so extreme that the standard model would struggle to produce it without changing assumptions? That is the scientific meaning of, does structure stop making sense? It is not a claim that the universe stops having patterns. It is a claim that beyond a certain scale, patterns stop being the best language for truth. The scale of homogeneity also pairs naturally with the future shaped by dark energy. The late 1990s supernova results, produced by teams led by Saul Perlmutter and by Brian Schmidt with Adam Rees, suggest that expansion is accelerating. In the standard lambda cold dark matter model, dark energy dominates the large-scale dynamics as the universe ages. That acceleration suppresses the growth of new structure on the largest scales. It does not erase existing clusters, but it makes the large-scale web less able to thicken over time. In a sense, dark energy locks in the homogeneity scale by reducing the ability of gravity to build ever larger coherent overdensities in the future. And this can be stated without alarm. It is simply a long-term sorting. Bound structures remain bound. Loose associations become looser. Filaments remain patterns, but their role as connectors weakens with time. The universe becomes, in a far future view, a set of isolated islands of bound matter, separated by expanding emptiness. In that future, largest structure becomes a more local phrase, because horizons shrink what can be seen and what can be influenced. So there is a kind of double limit. One limit is statistical, expressed by the homogeneity scale. The other limit is causal, expressed by horizons in an accelerating universe. Together, they explain why the universe has impressive structure, but not unlimited structure. Now comes the quieter part of the question. Not what is the scale of homogeneity in an abstract sense, but at what point does structure stop making sense to a human mind that evolved to count berries and watch weather? The first challenge is that the brain is comfortable with additive size, but not with multiplicative scale. Walking twice as far is easy to imagine. 10 times farther begins to feel vague. 1,000,000 times farther is no longer imagination in the everyday sense. It becomes a number on a page. Cosmic scales are not just large. They are scale changes piled on scale changes until intuition runs out of fuel. A planet is large compared to a person. A star is large compared to a planet. A galaxy is large compared to a star system. A cluster is large compared to a galaxy. A filament is large compared to a cluster. A great wall is large compared to a filament segment. Then the observable universe is large compared to all of them. Each step is not a gentle increase. It is a leap across orders of magnitude. The second challenge is that the universe does not give clean boundaries at these scales. The Milky Way has a bright disk, but its halo fades outward. A galaxy cluster has a core and an extended halo, and its boundary depends on a chosen density threshold. A supercluster can be drawn by density or by flow, and both are reasonable but not identical. A great wall can be outlined by a clustering algorithm and a threshold choice, and different choices produce different extents. Once homogeneity becomes relevant, the boundary is no longer a physical edge. It is a contour in a statistical field. This is why structure can stop making sense without stopping being real. The mind wants edges. The universe offers gradients. The mind wants single objects. the universe offers networks. The mind wants a largest thing like a single champion. The universe offers multiple categories that are each meaningful under different definitions. It helps here to be very explicit about those categories, because confusion often comes from mixing them. There are gravitationally bound structures like galaxy clusters, whose parts are held together over cosmic time by gravity. There are extended overdense patterns like superclusters and great walls, which are real features of the cosmic web but not bound as single units. There is the observable universe, which is the largest causally connected region visible from here, defined by horizons rather than by binding or overdensity. And beyond that, there may be more universe. Perhaps far more, but it remains beyond direct observation from this vantage point. None of these categories cancels the others. They answer different versions of the same question. So when the question is asked in the most physically concrete way, the answer is the largest gravitationally bound structures, meaning the most massive galaxy clusters. These are the largest things that behave like things, held together as unified systems. They can be mapped, weighed, and predicted to persist, even in an accelerating universe. When the question is asked in the most visually satisfying way, the answer shifts to the largest identifiable structures in the cosmic web, meaning the most extended overdensities traced in galaxy surveys like the Sloan Great Wall, and to debated candidates inferred by sparser tracers, like the Hercules Corona Borealis feature. These are the largest patterns that can be outlined in the distribution of matter, but they are not objects in the same sense as clusters. When the question is asked in the broadest definitional way, the answer becomes the observable universe itself, the 93 billion light-year diameter region within which all known structure is contained. It is a real physical concept grounded in relativity and causality, but it is not a bound object. It is a horizon defined by time. And when the question is asked in the deepest philosophical way, the answer becomes the scale of homogeneity, the point where the universe stops rewarding object language and starts rewarding statistical language. That is not a surrender. It is the most honest description of what the universe is on its largest scales. There is also a quiet emotional point that follows naturally from the science without needing to dramatize it. The largest structures are not built by intention. They are built by patience. A tiny early fluctuation becomes a slightly denser region. That region grows, it draws in more matter. It becomes a filament. Filaments feed clusters. Clusters merge. Ridges form. Great walls appear as extended overdensities. And then, above a certain scale, the whole pattern blends into an average again, because the universe began nearly smooth and remains nearly smooth when viewed broadly enough. That is the strange beauty of it. The universe is both intricate and simple. It is intricate when close enough to see the web. It is simple when far enough away that the web becomes a texture. So at what point does structure stop making sense? It stops making sense at the point where the map becomes more definition than discovery, where the boundaries depend more on thresholds than on gravity, and where the most truthful statements are statistical rather than pictorial. That point is tied to the scale of homogeneity, reached on the order of several 100 million light years, and certainly well before the size of the observable universe. It is not that the universe becomes featureless, it is that the universe becomes, in the large-scale view, fair. overdensities and underdensities balance, the mean density becomes meaningful. The cosmological principle becomes a practical description rather than an assumption. The universe, on its largest scales, stops looking like a collection of giant objects and starts looking like the outcome of a random field shaped by gravity. And that brings the journey into its final posture. The question began as a hunt for a champion. It ends as a set of definitions applied cleanly, with the universe refusing to give a single answer unless the question itself is made precise. The last step is not to introduce new candidates. It is to settle the ones already named, apply the definitions without flinching, and let the answer land with the right kind of calm. Now, the candidates can be placed on the same table without forcing them to compete unfairly. The universe is not refusing to answer. It is simply insisting that the question be asked in a way that respects physics. And once the definitions are kept clean, the answers fall into place with surprising steadiness. If the word thing means a single object held together by its own gravity, then the largest things in the universe are massive galaxy clusters. These are the biggest structures that behave like a unified system. Their galaxies orbit within the same gravitational potential. Their hot intracluster gas is trapped and heated to tens of millions of degrees. Their total mass, dominated by dark matter, can reach several quadrillion times the mass of the Sun. They are not just big arrangements. They are gravitational wells deep enough to keep their contents bound over cosmic timescales, even as the universe continues to expand. This answer is not glamorous in the headline sense because it does not have the drama of a wall stretching across a large fraction of the sky. But it is the most physically concrete answer. It is the one that survives the hardest test of all, the test of time. In an accelerating universe dominated by dark energy, the largest bound systems remain bound. Over extremely long times, the universe will not become one giant connected structure. It will become a collection of gravitational islands, with galaxy clusters among the largest and most enduring of those islands. If the word thing means the largest identifiable structure in the distribution of galaxies, even if it is not gravitationally bound as one unit, then the answer changes. Now, the cosmic web becomes the stage, and the question becomes a search for the most extreme overdensities within that web. In this category, structures like the Sloan Great Wall belong. They are not single objects in the gravitational sense. They do not share a unified gravitational center, but they are real features in the matter distribution, traced directly by galaxy positions and redshifts in large surveys such as the Sloan Digital Sky Survey. They can be outlined as extended ridges of higher density within the cosmic web, spanning around 1 billion light-years. Their existence is not a contradiction of the cosmological principle because homogeneity is statistical, not absolute. A universe can be statistically homogeneous at large scales while still containing rare, dramatic ridges within that statistical landscape. In the same category, the proposed Hercules Corona Borealis Great Wall sits as a more uncertain candidate. It is inferred not from dense galaxy mapping, but from the distribution of gamma-ray bursts detected by instruments such as NASA's Swift Observatory. Gamma-ray bursts are powerful beacons visible across great distances, but they are rare, and their catalogue is shaped by strong selection effects and incomplete sampling. That does not make the idea meaningless. It makes it harder to confirm. If a clustering of bursts suggests an enormous overdensity, the claim must survive statistical scrutiny that accounts for observational bias, sparse sampling, and cosmic variance. So this proposed wall remains an intriguing possibility rather than a settled cornerstone of the cosmic map. The crucial point is that both kinds of answers can be true at the same time, because they answer different versions of the question. A galaxy cluster is a thing in the gravitational sense. A great wall is a thing in the statistical structure sense. The universe is not obligated to give only one category of largest, because the word thing itself carries multiple meanings when scaled to cosmic size. If the word thing means the largest region that can be described at all from this vantage point, then the observable universe enters the table. The observable universe is not a bound object. It is a horizon defined by causality, by the finite speed of light, and by the finite age of cosmic expansion. Its present-day diameter is about 93 billion light-years, larger than first intuition expects because space has expanded while light was traveling. This is not a physical edge. It is a boundary of what can be seen from here. Another observer elsewhere has another horizon. So the observable universe is the largest definable region from this location, but it is not a single object produced by structure formation. It is the stage limit, not the stage prop. And then there is the deepest version of the question, the one that was hinted at from the start. At what point does structure stop making sense? The answer is not a single number carved into space-time. It is a transition in the kind of statements that remain honest. Below a certain scale, the universe is best described in object language. Planets, stars, galaxies, clusters. These have strong physical cohesion and can be measured as discrete systems. As the scale grows, object language becomes less faithful. Superclusters become partly bound, partly transitional, and partly definitional. Great walls become extended over densities whose boundaries depend on thresholds and clustering algorithms. Beyond that, homogeneity emerges, and the universe becomes best described statistically as a density field with fluctuations whose significance is measured by probability rather than by outline. This is where the scale of homogeneity matters. It is the scale at which, when averaged over sufficiently large volumes, the universe approaches the same mean density everywhere. It is supported by the near uniformity of the cosmic microwave background, mapped by missions such as the Planck satellite, where the early fluctuations were tiny, only a few parts in 100,000. Those fluctuations were amplified by gravity into the cosmic web, but the amplification has limits. Dark energy inferred from Type 1a supernova studies by the teams led by Saul Perlmutter and by Brian Schmidt with Adam Rees further limits the growth of new large-scale structure by accelerating expansion. The universe builds, but it does not build without restraint. So the place where structure stops making sense is the place where the map becomes more about definition than about discovery, where the boundaries depend more on chosen thresholds than on gravitational unity, and where the most truthful questions become statistical. How significant is this overdensity compared to random expectation? How often do simulations like the Millennium Simulation produce features of this size under the lambda cold dark matter model? How much does cosmic variance limit certainty on the largest scales? How much do selection effects shape what appears in the dataset? In that framing, the largest structures are not trophies. They are tests. They test the statistical character of the universe, the validity of the cosmological principle, and the connection between early universe fluctuations and late time structure. They also test the human mind's preference for clean edges, because the universe does not provide them. And that leaves one final step. Not a new fact, but a clean landing. The universe is simultaneously structured and smooth. It is structured in the way a coastline is structured, full of bays and inlets when seen up close. It is smooth in the way a planet is smooth when seen from far enough away, where mountains become texture and coastlines become a line. On small scales, gravity creates islands of matter, bound systems that persist. On intermediate scales, gravity creates networks, filaments, and walls that are real patterns, but not necessarily permanent unified objects. On the largest scales, the universe approaches statistical homogeneity, where structure exists, but the concept of the largest thing becomes a question of definitions and probabilities rather than of a single named object. So if the question is asked plainly, with no tricks, the answers are these. The largest gravitationally bound things are massive galaxy clusters, held together by dark matter halos, seen through galaxy motions, hot X-ray gas, and gravitational lensing. These are the biggest structures that behave like coherent objects. The largest identifiable patterns in the distribution of matter include features like the Sloan Great Wall, and possibly larger debated features inferred by tracers such as gamma-ray bursts, though those claims require careful statistical confirmation. These are the biggest structures in the sense of extended overdensities within the cosmic web. The largest region that can be defined from here is the observable universe, a horizon limited by light travel time and cosmic expansion, containing everything that can be observed from this vantage point. And the point where structure stops making sense is the point where object language yields to statistical language, where the universe becomes better described by homogeneity, correlation functions, power spectra, and the probability of extreme fluctuations rather than by the edges of a single shape. The strange comfort in all of this is that the universe remains consistent. It does not change its rules just because scales become absurd. Gravity keeps doing what gravity does. Expansion keeps stretching space. Dark matter keeps building scaffolds. Dark energy keeps limiting growth. Inflation, if the broad picture is correct, seeded the entire hierarchy with tiny quantum fluctuations stretched to cosmic size. The same small beginnings produce the largest structures, and the same large-scale limits prevent those structures from becoming infinite. So the largest things in the universe are not only large, they are instructive. They show how far a nearly smooth universe can go in creating pattern before it returns, at the larger scales, to smoothness again. And once that is understood, the question no longer feels like a hunt for a single champion. It feels like a map of what the universe allows. A hierarchy built by gravity, a boundary drawn by horizons, and a quiet line, somewhere out beyond the great walls, where structure becomes less like an object and more like a statistical whisper spread across the dark.